Hello and welcome to the makeup video for Unit 8's lab, Thermochemistry of Candles. Purpose: during this lab you will be investigating the efficiency of using a candle to heat a known quantity of water. Thermochemistry and calorimetry are required to evaluate the heat released by the candle compared to the heat absorbed by the water in the lab. The percent error formula will then act as a comparison between the two values. Background: heat changes are an important part of everyday life. Here in the desert, most people strive to conserve energy in order to conserve our natural resources. The use of energy-efficient appliances, from audio and video electronics to large appliances like air conditioners, heaters, and refrigerators, over the less efficient versions, not only saves money, but is also promoted by local, state, and federal governments. This idea can be extended to a simple yet powerful lab experiment that takes a known mass of a substance, wax, that is burned to release energy to determine the quantity of heat energy released. This heat is compared to the heat that a known mass of water absorbs according to the no phase change equation. The difference between these energy values allows the determination of the efficiency of the process using the percent error formula. We have as some information the thermochemical equation for the reaction. C20H42 plus 30.5O2 yields 20 CO2 plus 21 H2O plus 11,900 kilojoules. We utilize the no phase change equation, Q equals M times Cp times delta T, and the percent error formula is the absolute value of experimental minus theoretical divided by the theoretical value, and that times 100. We're going to make use of the equipment and materials listed there. We have a beaker, and we first have to get the mass of the beaker and record that mass on the actual data table. For initial beaker mass, we have the candle mass also given, beaker plus water mass, initial water temperature, all those taken before the heating process, and then at the end of the lab experiment during the after heating, final water temperature and final candle mass. The values on the right side of the data table, those ones are going to be calculated from information over from the left. So measuring the initial candle mass, we have a small candle measuring its mass. We have 8.2 grams. So 8.2 grams, the initial candle mass, record that in that spot, 8.2 G. Getting the beaker mass, the mass of the beaker is 60.7 grams. According to the procedure, we have to fill the beaker with water to the 80 milliliter line. I have approximately 80 milliliters of water in this graduated cylinder that I'll pour into that beaker. It looks like it's pretty much right on that 80 milliliter line. Now I'm going to get the mass of the beaker plus the water. And this is going to be recorded where it says beaker plus water mass, 140.5 grams G. Now we have to measure the nearest, or to the nearest 0.5 degrees Celsius, the temperature of the water as indicating in step 3. So I have this flask with this thermometer in it. I'm just going to put that thermometer into the water. Of course, the temperature of the room is what the thermometer was reading, and then the water close to, if not right on, that room temperature value. It looks like we have a pretty stable reading for our thermometer, and we want to record this temperature as the initial water temperature and record 23.0, and that'll be degrees Celsius. And replacing the thermometer into the flask for safe storage of that flask. At this point, we're going to take the beaker with water and put it on the pipe stem triangle. Light the candle. and place the candle underneath the beaker. The procedure says to heat the candle for 10 minutes. So starting my timer for 10 minutes. Before perhaps skipping ahead approximately 9 or so minutes into the video, let's talk about some of these questions. Number 1, it talks about showing the work for the calculated data above. And for that, that's basically the calculation of the water mass which is right here. Of course, we're going to need for the water mass to take the beaker plus water, which was the 140.5, and subtract from that the mass of the beaker to get the water mass. So that's going to be a calculated value. That is the only one we can calculate at this point. The other two, the mass of the candle burned and the delta T of the water, we have to wait for the end of the heating process. So it says show your work for the calculated data above, below each of the three values. So then for water mass, right underneath there, we have 140.5 minus 60.7, and then that's going to equal, let me grab a calculator. (140.5) minus 60.7, 79.8. So 79.8 grams is the mass of the H2O that's in that beaker being heated currently. So we'll do the same thing with the mass of the candle burn once we have the final candle mass, and we'll be able to calculate the delta T of the water once we have the final temperature of the water. Number 2 for the question asks, is the burning of the candle endothermic or exothermic, and why? So the burning process, of course, would be specifically the actual flame on the candle and the burning process there. There's other stuff that's happening there, but the burning process is the process that's in question. Kind of think of a Bunsen burner flame and what's happening with that, heat out versus heat in, and exothermic versus endothermic. And be sure to explain the why. So for 3, calculate the quantity of moles of candle wax burned. So not only do you need to use the molecular formula to get the molar mass of the wax, so you want to see the equation on the front to get the formula for the wax. It's a pretty big formula. You'll be in the couple of hundreds for the molar mass value. Other than that, you're converting from grams to moles. And the substance in question is the wax. And that mass of candle burned will allow you to get from grams to moles. Number 4, calculating the amount of heat that the combustion of the candle released in kilojoules. So for that one, you want to, once you have the moles, so number 4's answer, and that's going to be moles. You got to convert that into kilojoules. So number 4's answer, that's going to be moles. Convert that to kilojoules. For that, you want to use the generic equivalent statement of A moles of A equals number sign, kilojoules. Of course, you want to use this base for your solution. Here, I'm just telling you what you want to use. That's going to give you a number in kilojoules, of course, as your answer if you have the setup appropriate. And then for number 5, you're taking, oh, mistake right here, this should be number 3. So for number 5, that's the answer from number 4, and of course that's going to be kilojoules, and you want to convert that into joules. You want to use 1,000 joules equals 1 kilojoule. and then that's going to attract the heat that's released by the burning of the candle. For number 6, it's saying use the no phase change equation to calculate the Q absorbed by water in joules, and that equation is given on the front of the lab, and it's the Q equals mCp delta T, all multiplied together. But your substance in question is the water, H2O. You do not want to use the mass of the candle for your M, but you want to use the mass of the water, and that's calculated up here, 79.8. You're multiplying by the specific heat capacity of the water. It's specifying here joules, so you want to use the joules version for the specific heat capacity of liquid water. And you're multiplying by your delta T. The delta T, like the mass, is obtained up here. So here you see the delta T of the water. So you need the final water temperature and subtract from that the initial water temperature to get your delta T. That'll be once heating is done. For number 7, it's asking for the total heat absorbed by the water in kilojoules. Your answer for number 6 is going to be in joules. So you want to convert that into kilojoules. It's almost the reverse process of number 5. Well, it is the reverse process of number 5. You want to use 1,000 joules equals 1 kilojoule. Of course, 1 goes on top, 1 goes on the bottom, so that you end up with kilojoules for your answer. For number 8, getting the difference there, it says the experimental value is the Q for the water. In other words, the EXP is the value you get from number 6, and the theoretical, the THEO, that's the value you get from number 5. Both of these, 6 and 5, are the joules versions of each of those heat values. We could have also used number 7 with number 4. The difference is that that would be KJ and KJ. It doesn't matter which one you use as long as they match. Here, they match. So then you just fill in those values of Q from 6 and 5 into the formula that we see here in the front. And that's the experimental, that's the water one, minus the theoretical, that's the one we found first, and then absolute value of that. So if you have a negative sign, it's ignored. Divide that by your theoretical value, and then you take that and you multiply by 100, and then you'll have a number between 0 and 100 as your percentage. It's probably going to be a little on the higher side, probably upwards of 2/3 or 3/4 of percentage, so it's anywhere from 65 to 80, somewhere in there. And that would then be your heat that's lost. That means whatever that percentage is, probably going to be pretty big. Most of the heat was gone. Then the question remains then, where did all that heat that didn't get into the water go? And that's what number 9 is asking about, and explain in your own words the reasons why the percent error is what it is. And then that's what you want to put there for number 9. Make sure you have complete thoughts and sentences there in your answer for number 9, where else the heat went. About a minute and a half left on heating. Continue to watch or skipping forward if you so desire. As we approach this, the end of this final minute, what we're going to do at the conclusion of the 10 minutes is blow out the candle, carefully remove the beaker from the pipe stem triangle, allow the candle to cool, and then immediately measure the temperature of the water. So I'm going to use the thermometer to stir that water around so that you get a nice even distribution of the hotter water from the bottom to the cooler water that's on the top in that beaker. So to kind of mix it all around, get a nice even temperature. So I'm going to want to get a read within about 30 to 60 seconds, no longer than 60 seconds, but as soon as possible. And then get the mass to the nearest 0.1 grams when that candle wax solidifies. And then that'll be our conclusion. And we are approaching the end of our time here. Blow out our candle. Carefully remove the beaker. Grab the thermometer. Gently stir it around. Get a nice mix. Thermometer is pretty fast and accurate. So in that mixing there, I can see I do have an elevation in my temperature. Looks like it's still climbing. It's slowed down. And it looks like it's not moving anymore. Get that final temperature read, because of course the water is cooling off at this point. Alright, looks like it's no longer climbing. It's actually dropped just a little bit. So we're going to say our final temperature reading. So then in the data table on the left, final water temperature, you want to record that as 34.5. 34.5 for final water temperature. And that would be degrees Celsius. Our candle looks pretty good with respect to the wax solidifying a little bit. So it's not spilling and pooling all around, but it has kind of congealed. Putting the candle there on the balance. The mass, 7.8 grams. So we now have our final temperature and our final mass. For your mass of your candle burn, you want to take your 8.2 and subtract from that your 7.8, so we're just under half a gram. And for the delta T of the water, you want to take your 34.5 and subtract from that your 23.0. So just over 11 degrees Celsius temperature change. So you want to include that 0.5 in there. And then go through those calculations and get this submitted to your teacher on the date designated. Thank you, and that was the makeup lab for Unit 8. Thermochemistry of Candles.